Hello friends, I welcome you in lecture number 3 on roots of equations. In lecture number 1 and 2, we have discussed about bisection method. We have discussed the idea of bisection method and we have seen one question on finding the root of equation using bisection method. In this lecture also we will solve one equation using bisection method and we will try to find out its root which is correct up to 4 decimal places. This question was asked in GTU Summer 2022 exam of AME subject. First we read this question, discuss bisection method. So we have already discussed bisection method in lecture number 1. So you can write that description from lecture number 1. Find a root of x cube minus x minus 11 equal to 0 correct to 4 decimal places using bisection method. So here given equation is third degree polynomial equation and it is non-linear equation. So we have to find out its root correct up to 4 decimal places. So we can fix our calculator either up to 4 decimal places or greater than 4 decimal places, and we will continue with our bisection method unless we obtain two successive approximations which are equal up to 4 decimal places. I have done all my calculations using scientific calculator and fixing it up to 4 decimal places. If you wish, you can fix your calculator up to 5 decimal places and then at each step you can compare your successive approximations up to 4 decimal places. Now as we know, we have to first consider our equation in this form. To apply bisection method, first we have to write our equation in this form, some function of x equal to 0, and it is already given in this form. So we can consider fx equal to x cube minus x minus 11. Now the bisection method says that if you can find out by trial and error 2 points A and B such that f of A and f of B are of opposite signs, then root of given equation always lies in between A and B. So the bisection method in fact searches for the interval in which our exact root lies. So for that we have to just start with two real numbers A and B such that f of A and f of B have opposite signs. So by trial and error I have obtained 2 points. First I have taken x equal to 0, and if I put x equal to 0 here I get minus 11, that is negative. Then I tried for x equal to 1 and I obtained f of 1 is also minus 11, which is negative. Then I put f of x equal to 2, that is f of 2, and I obtain 2 raised to 3, that is 8 minus 2 minus 11, which is also negative. And for x equal to 3 I obtain 3 raised to 3, that is 27 minus 3 minus 11, which is 13, and it is positive. So I have obtained 2 points such that f of 2 is negative and f of 3 is positive. Therefore our search interval is 2, 3. Our root lies somewhere in between 2 and 3, that is intermediate value theorem. Here our function is continuous and f of 2 and f of 3 are of negative signs, therefore root lies in between 2 and 3. Now the bisection method says that you have to consider midpoint of this interval as the first approximation. So that is 2 plus 3 divided by 2, which is 5 by 2, that is 2.5. So this is the first approximation. We are bisecting our interval 2, 3, that means we are finding the midpoint of this interval, which is average of 2 and 3. So the first approximation is x1 equal to 2 plus 3 divided by 2, which is 2.5. Then we find out value of function at point 2.5 and we check whether it is positive or negative. So I have calculated f of x1, which is f of 2.5, and I using this formula of given function is x cube minus x minus 11. Here I put x equal to 2.5 and I find that it is positive. F of x1 is positive. So f of 2.5 is positive and it is the average of these 2 points, 2 and 3. So I have to consider the point for which function is negative. 2.5 is obtained by taking average of 2 and 3, and f of 2.5 is positive. So out of these 2 points I will consider that point for which value of function is negative. So that point is x equal to 2. We have obtained f of 2 and f of 3, and we find that f of 2 is negative and f of 3 is positive, and f of 2.5 is positive. Therefore I have to consider 2 and 2.5 for the next approximation. So the next approximation is average of 2 and 2.5. So in fact we are going in this way. F of 2 is negative, f of 3 is positive. This is our first approximation, 2.5, and f of 2.5 is positive. So root cannot lie in this interval. So root must lie in between 2 and 2.5 because f of 2 is negative and f of 2.5 is positive. So our next approximation is average of 2 and 2.5. So that we denote by x2. Therefore the second approximation is x2 equal to average of 2 and 2.5, that is 2.25. Now we obtain value of function at 2.25. So that for that again we use that formula of x equal to x cube minus x minus 11, and using scientific calculator I obtain this value. That means value of function at 2.25 is negative. So out of these 2 points I have to consider that point for which function is positive, and here we know that f of 2.5 is positive. So next approximation will be average of 2.5 and 2.25, that is the third approximation. x3 equal to 2.25 plus 2.5 divided by 2, that is 2.3750. And at each stage we have to compare our approximation to the preceding approximation. Second approximation is 2.25, third approximation is 2.3750. So they are equal up to 0 decimal places, we can say that. So now I have to go up to 4 decimal places. So I will stop my procedure when I obtain 2 successive approximations which are equal up to 4 decimal places. So I have to go for fourth approximation. So again I find out value of function at point x3, and it turns out to be positive, and x3 is average of 2.5 and 2.25, and f of x3 is positive, and I have to check whether f of 2.5 is positive or f of 2.25 is negative. So this is negative. This is average of these two, and value of function at 2.3750 is positive. So I am considering 2.25 for the next approximation because value of function at 2.25 is negative and value of function at 2.3750 is positive. So next approximation is average of 2.3750 and 2.25. So that will be our x4. So at each iteration what you have to keep in mind that whatever approximation you obtain, find out value of function at that point and check whether it is positive or negative. If it is positive, then find out the point for which function is negative. Here f of 2.3750 is positive, and out of these two f of 2.25 is negative. So my next approximation will be average of 2.3750 and 2.25, that is denoted by x4. and I obtain 2.3125. So we can compare x3 and x4, they are equal up to only first decimal place. So I have to continue this process. After that I find out value of function at x4 and it turns out to be negative. Value of function at this point is negative. So I have to check for which point out of these two function is positive, and we know that function is positive at this point 2.3750, and at this point function is negative. So we take average of these two as our next approximation. So x5 is 2.3125. So at this point function is negative, plus 2.3750, at that point function is positive. So this is our fifth approximation, and I compare with this, then they are not equal. So I continue with value of function at point x5, and I obtain that f of x5 is negative, and f of 2.3125, this point, at this point function is negative, and at this point function is positive. So we will consider next approximation as average of 2.3750 and 2.3438. So that is 2.3594, and we can compare x5 and x6, they are different. So again I repeat the same process. I obtain value of function at point 2.3594 and it turns out to be negative, and at this point function is positive. So next approximation is average of these 2 points. So in this way I have calculated all the upcoming approximations, and I find that the number x14 and x15, these two are equal up to 4 decimal places. So you have to continue this process up to 15th approximation, and you will find that x14 and x15 agree up to 4 decimal places. So therefore the root of given equation correct up to 4 decimal places is 2.3737. So you have to continue in this way every time. What is the idea of the method? Simple, it is very simple. You just find out 2 points A and B such that function is negative at one point and positive at another point. Suppose function is positive at point A and negative at point B. Then consider this AB as your search interval. Then we are making bisection of search interval at each step. So we consider midpoint of this interval, which is x1 equal to a plus b by 2, and it will divide this interval into two subintervals of equal length. Then we check what is value of function at x1. So suppose value of function at x1 is negative, then root cannot lie in this part because f of x1 and f of b both are negative. So our search interval becomes this part, a to x1. This is our search interval now. So again we take bisection of this interval. We consider average of a and x1, and that is x2 say, and we then find out value of function at x2. Suppose f of x2 is positive, then root cannot lie in this interval. So our search interval becomes x2 to x1. So again we take bisection of this interval. We denote next approximation by x3. So in this way we are converging to the exact root. The process is slow, but we are sure that we are going near to the exact root in this way. So here in this for this equation I have to go up to 15th approximation to obtain my root up to correct up to 4 decimal places. So be patient, keep patience while you are doing this bisection method, and be careful about calculations. If there is a single mistake in any calculation, then all your succeeding approximations might go wrong. So this is all about this session. I hope you like it. Thanks for watching.